Okay, everybody, here we go. We're going to talk about the standard normal model. Okay, first we want to review the 68, 95, 99.7 rule. Again, here's the picture. There's not much to say about it. One standard deviation to the left, one to the right is 68%, to the left, to the right is 95%, 99.7 between -3 and 3. The drawback to this is that it's a little bit, it's not terribly precise, and we can only talk about standard deviations from -3 all the way to +3. We can't ask about z-scores of like 2.7, for instance. So here's the standard normal curve. The standard normal curve is just a normal curve, except that the value at 0 is a z-score of 0. Okay? A value of 1 is a z-score of 1. A value of 2 is a z-score of 2, and so on. So it's basically taking a normal curve and making all the z-scores be the x values on the bottom. Okay, so let's review normal curves for a moment here. Every normal curve, not just the standard normal curve, is uniquely defined by its mean and its standard deviation. Okay. Oftentimes we'll have a shorthand, capital N with the mean and the standard deviation there. That way we don't have to write out every time, this is a normal curve with a mean of and a standard deviation of. Instead we can just write it as N with the numbers in there. Okay, so here's an example, and we're going to get to the standard normal curve from this in a moment. If the basketball team's average height is 77 inches with a standard deviation of 5 inches and their heights are normally distributed, then we can use that shorthand to describe the distribution. It's pretty straightforward, I think. Okay, the question we're asking here is what percentage of players are between 72 and 82 inches tall? Okay, well, with the 68, 95, 99.7 rule, this isn't so hard to answer. Okay, same thing, what percentage are taller than 87 inches tall? Okay, again, not so hard to answer. You notice that 72 and 82 are 1 standard deviation to the left, 1 to the right. 87 inches is 2 standard deviations to the right. Okay, so we can apply that 68, 99.7, 68, 95, 99.7 rule. But what about if we ask about percentage that are shorter than 79 inches tall? Now 79, if we go back, okay, 79 is less than 1 standard deviation to the right. Okay, so we can't use that 68, 95, 99.7 rule. Okay, so we need new tools. What we're going to do is we're going to start by looking at the z-score. Okay, here's the formula for z-score. Notice now that I'm using x minus mu divided by sigma rather than x minus x bar divided by s. Remember last time I said that mu is the same as x bar except that it's like a theoretical x bar, and sigma is the same as s except that it's a theoretical s. So for the most part, for most of what we do, we can think about mu and x bar as being interchangeable, and for the most part we can also think of x bar and sigma, or sorry, s and sigma as being interchangeable. Okay, in some sense. Okay. We sometimes call the z-score a standardized score, and that's just because when we think about it, we could have 2 different distributions, and both distributions could be completely different, and yet I can get a z-score equal to 1 on one distribution, and another z-score also equal to 1 on the other distribution, and in some sense those two have similar properties, so we've standardized them onto a new scale, the z-score scale. All right. The question I want to ask now is, what if I transform all the data into z's? What if I take every single basketball player and I compute the z-scores for every single one of them, and then I plot that distribution? Okay, rather than asking, okay, what's the z-score for the player who is 79 inches tall? What if I say, let's just go ahead and we'll take the z-score for everybody? Okay, what that means is that the average, the value that was the average, it now has a z-score of 0, so we're going to plot that in the middle. Okay, the player who is exactly 1 standard deviation from the mean, so the player who is we had 77, 82. Okay, the player who is 82 inches tall now has a value of 1 because he's 1 standard deviation above the mean. Okay, so any value that is at 1 standard deviation to the right has a z-score of 1. Okay, and therefore is at 1 on the new axis. And to the left, the same thing is going to happen. Okay, So what we do is we not just standardize an individual player, now we standardize the entire normal curve, and hence the name standard normal curve. Okay. And again, the standard normal curve is a normal curve with a mean of 0 and a standard deviation of 1. Okay? So whenever you look at a normal curve that has a mean and average value of 0 and a standard deviation of 1, that's the standard normal curve. Okay, and why is it useful? That should always be your question you ask, especially in this course. Why is it useful? Okay, and the reason is because it's so easy to use, right? If I want to find out what the value, how far to the left do I have to go to get to 3 standard deviations? -3. Okay, it's pretty easy. If I go 1.5 standard deviations to the right of the mean, the value on the x-axis now, what we'll call the z-axis, is just 1.5. Okay, and now I can say, and it gets cut off at the bottom here, what area lies between -1 and +1? Well, by the empirical rule, 68%. Okay, so it just makes things easier. Instead of having to transform everything to z-scores, it's already in z-scores. All right, so again, why should we care? That's a good question to always ask in this class. So, what if we wanted to know, back to that original question, what the percentage of players on that basketball team were shorter than 79 inches tall? Okay, back to the original question. Okay, well, we have a mean of 77 and a standard deviation of 5, and it's normally distributed. 79 is less than 1 standard deviation to the right of the mean, so we can't use our favorite rule. We have to get some new tools, like I was saying before. And here's what we're going to do. We're going to standardize everything to make life simpler. Okay? So every datum gets transformed by that equation there, including the mean, including the standard deviation, and including the player who was 79 inches tall. Okay? So the mean was 77 is now 0. The standard deviation that was 5 is now 1. And the player who is 79 inches tall now is a value of 0.4 on this new scale. Okay? So everything gets shifted. So 79 is transformed to 0.4. So the percentage to the left of on the original curve, on the left of 79 in the original curve, is the same as the percentage to the left of 0.4 in the new curve. That's an important point. That's where we're going with this. 75 on the original curve, if I ask about what proportion of players are less than 79 inches tall, it's the same question as asking what proportion of the data are to the left of 0.4 on the standard normal curve. That's where we're going with this. Okay. If you can make that conceptual leap, then you should feel pretty good about this. That's what we're going for. So now, let's try to figure out what the percentage to the left of 0.4 is on the standard normal curve. So that's the question we're trying to solve. If we solve that question, we've solved the original question. So this is what we need to solve. The integral from -∞ to 0.4 of that business right there. And notice I've plugged in here, if you remember the equation from last time, I've plugged in sigma equal to 1 and mu equal to 0. So it's a much easier integral to solve here. Okay, but we're still integrating from -∞ to 0.4. And if you're not familiar with calculus, this is complete gibberish to you. All right, and that's okay. All right. Now, move along here. There we go. So, the great thing about this equation is that this equation will solve the problem for any distribution where I'm asking about something that is a z-score of 0.4. Okay, so that means that if I have any other distribution, whether it be batting averages or heights or weights or whatever it is, and I find that I want to know about something with a z-score of 0.4, I'm going to use this distribution. Sorry, I'm going to use this equation to solve that problem. Okay, so this equation solves a lot of problems for us. Okay, as long as we transform everything to the standard normal curve. All right. So this is the equation I'm trying to solve. Okay, and yeah, we can use our calculators. We can get crazy with our integral calculus. Okay, and this is going to solve not just the problem we had, but it's going to solve the area to the left of the number 6 on that equation. Okay, but again, it would really suck to have to integrate that integral. That's just not fun to do. Okay, and the point of this class is not to be able to integrate; it's to be able to solve real-world problems. We're trying to figure out what proportion of players is less than 79 inches tall. That was the original question we're trying to solve. Okay, so you can try to do it again, but I'm not going to try to do it. I don't want to do it. Okay, I've never tried to do it. So the point is we let someone else do it. Okay, and what's happened over time is that other people have solved it, and then we've created a table. That's one way to solve it, and we've created calculator programs to solve it for us as well. Okay, so we don't have to go through that work because that's not the interesting work in this class. So, right now I'd like you to take a look at your textbook, okay, and look at the front of the book. I believe it's in the front of the book for the table, and I'm going to go and pull it up on the computer here. Okay, there it is. So this is the table you should see in your book here, Table A. Now, the way this table is read is you have a normal curve like this, okay, and at the bottom you have the z-score, okay, and it's going to give us, the entry in the table is going to give us the area to the left of that z-score. All right, and notice what we have here. We have z's on the left, and then numbers across, and then areas in here. So every one of these are an area. We're looking for a z-score of 0.4, so I'm going to scroll down, not on this page, these are all negative numbers. Aha, 0.4, right there. Now, that's the number I'm looking for. I want 0.40. So I'm going to go 0.40. 0.41 would be right here. So if my z-score had been 0.41, I'd go 0.41, and this would be my answer. 0.42, this would be my answer. 0.43, this would be my answer, and so on. My answer, however, is 0.6554. That's the area. Now remember, the area underneath the normal curve is 1. So this is 65.54%. This area here to the left of 0.4. All right? 65.54%. All right, let's go back. Okay. So we just look it up in the back of the book, or the front of the book actually. They've changed the table. Okay. So the area is 65.54%. 65.54% of basketball players on this team are less than 79 inches tall because 79 inches tall is a z-score of 0.4, and then the z-score table is in the book. Okay, so what if we want to find the percentage of basketball players between 70 and 79 inches tall? All right. What we're going to do here is we're going to find the area to the left of 70 and the area to the left of 79 and subtract the two. Okay, this is an important point because if you look at the table only gives you areas to the left of z. So if I want to find areas to the right of z, I have to remember that this entire area is 1. So if I want to find the area to the right of z, I'm going to do 1 minus this area. If I want to find the value between two areas, pardon me, between two areas, between there and there, I need to find the area to the left of this and the area to the left of this and subtract the two in order to find the area in between. Okay, so that's pretty important stuff. All right. All right. Now, I used to make you do it using the table in the book. No more. Okay. We use the calculator to do just about everything. The calculator replicates what's in the table. Some people love using the table, in which case, by all means, use the table. It's great. It really is wonderful, and it will help you understand what's going on. But the calculator can do the same thing, and it's actually easier and it's actually more accurate. So here's how we do it. We follow these keystrokes. Second vars, and we find normal CDF. Okay. Normal CDF, the way we put it in is we put in the lower number and the upper number. Okay. So if we look for the area on the standard normal curve between -1 and 1, we should get about 68%. Let's see if that works. I'm going to pull up my Wabbit here. So I'm going to go second vars, normal CDF. What's the area between -1 and 1? Okay. On many calculators, you're going to be looking at putting this in. Okay. Just normal CDF, -1 to 1. And that's going to give you the area between a z-score of -1 and a z-score of 1. If I press enter, about 68%. Oh, okay. What about between -2 and 2? We should get about 95%. Yep. And negative 3 and 3. Okay, 99.7%. All right, now that's great if you're trying to find the area between two values. Okay, a height of 70 and a height of 77. Find the z-score for 70, find the z-score for 77, plug in. But what about the situation where I want to find just less than 79, greater than 79, less than 70, greater than 70? Okay, that's a little more complicated, but it's not that much worse. What we have to take advantage of is some calculator notation. Let's talk about solving the same question that we had before, where I was trying to find the area to the left of 0.4. Now here's what we're going to do. We're going to use a particular number as a stand-in for infinity. Okay, the stand-in for positive infinity will be 1 second comma, which is this little e, 99. What this does is creates an incredibly large positive number. It's a 1 with 99 zeros. Okay, press enter, you get the same thing. Negative infinity will be negative 1e 99. So that's your stand-in for positive infinity and your stand-in for negative infinity. So if I want to go ahead and find the area from 0.4 to the left, I'm going from negative infinity, so negative 1e 99 to 0.4, and now I get 0.6554, just like the table said. Okay. If I want to find 0.4 to positive infinity, I'm going to change these. Normal CDF, again, I can go second bars, and it'll be number 2. 0.4, comma, 1, this is positive infinity. And notice that 0.655429 plus this equal 1, because I'm looking to the left and to the right, and together they're the entire curve. So the sum of these two will be exactly 1. Okay, I think this is enough to get you guys going. So what we reviewed today is, what is the standard normal curve? Why is it useful? Okay, how to use the standard normal curve to compute probabilities, or to compute areas, using both the table and now using the calculator. Okay? All right, I think we're set to go, and we'll see you next time. Thank you.